Hello and welcome to our first video about section 4.3 in our calculus text. There's a lot going on in this section, so we're going to look at a couple of important results, look at some examples involving those results, and then we'll look at a number of examples where we're finding local maxes and local mins of several functions. But first, I want to introduce you to one of the more important results in calculus. It comes into play a couple of times in important spots in trying to understand other results. We'll see one of those in just a few minutes. And so we're looking at the mean value theorem. So you can read about the mean value theorem in your text, but I'll go ahead and state it here. The mean value theorem says if you have a function which is continuous on a closed interval from a to b and is differentiable, that means we can calculate a derivative on the open interval from a to b, then there exists a point C on the interval from a to b such that, and here's the equation, f prime of C is equal to f of b minus f of a over b minus a. And so let's just think about this for a minute. Derivatives measure slope of the tangent line. So this is the slope of the tangent line at some point on the curve. And over here, this is the slope of the secant line joining the points a f of a and b f of b. So what this result is saying is that as long as you've got a function which is continuous and has a derivative everywhere in between, that if you look at the slope of the secant line that joins the two endpoints of the interval, there's always going to be at least one point in between where the slope of the tangent line is equal to the slope of that secant line. And I've got a sketch down here which attempts to illustrate this. And so I'm taking this number right here as A and this number as B. In reality, in this picture, A is 1 and B is 10. But I want to think about this as the point A comma f of A. And I want to think about this as the point B comma f of B. And so the blue line here has slope f of b minus f of a over b minus a. And what the mean value theorem says is that there's at least one point in between a and b where the slope of this tangent line is equal to the slope of this blue line. And for this particular function, there are actually 2 points. And so if I look right here, say at this point, I'll call this C1. At C1, the slope of the tangent line is equal to the slope of the blue line, the secant line. Those lines are parallel, they have the same slope. And then I've got another one right down here. So it looks like C2, another value of C is right here. And so I've got these 2 points. In this particular case, we don't have to have 2, but there's at least one always, where the slope of the tangent line, or the tangent line is going to be parallel to the secant line that runs between those 2 points. So that's what the mean value theorem is saying, and I hope this graph is helping to illustrate, try to communicate what the content of this result is. So we're going to turn right around and use the mean value theorem to help us see an important result about how the sign of the derivative is related to the behavior of the function. And in particular, the sign of the derivative tells us whether a function is increasing or decreasing on an interval. So let's look at this My first statement is when the derivative is positive on an interval, that means that the function is increasing. So positive derivative implies increasing function. And then the second statement here, if the derivative is negative on an interval, then the function's decreasing. So a negative derivative tells us that we've got a decreasing function. So this is going to be something that we do a lot of in our examples. We're going to be examining the sign of the derivative, and we're going to be able to tell information about whether the function is increasing or decreasing on intervals. But let's take a moment to try to establish the truth of this statement. At least let's take the first one. Suppose that the derivative is positive. How can we argue that the function has to be increasing? So let's remember what it means for a function to be increasing. First of all, f is increasing means that larger inputs give larger outputs. So in other words, if x1, let's see, if x2 is bigger than x1, then f of x2 is going to be bigger than f of x1. So the larger input gave the larger output. So let's try to establish this statement. So we're assuming that a function, the derivative is always positive on the interval from a to b. So we're going to let x1 and x2 be two numbers such that x1 is less than x2 on the interval from a to b. So these are two numbers between a and b where we're taking x1 to be the smaller number. Okay, by the mean value theorem that we just established, or we just discussed, there exists a point C between x1 and x2 such that f of x2 minus f of x1 over x2 minus x1 is equal to f prime of c. And by assumption, f prime of c is a positive number because that's the value of the derivative at some point between between x1 and x2. Well, now let me multiply both sides of this equation by x2 minus x1. So we'll multiply both sides by x2 minus x1. Then I get f of x2 minus f of x1 equals f prime of c times x2 minus x1 greater than 0. Well, guess what? So this is actually true. This is positive by assumption, and this is positive by assumption. So their product is positive. So what that means then is that f of x2 minus f of x1 is also positive, or I can write this as f of x2 greater than f of x1, which tells me that f is increasing. We would do something similar to establish the truth of the second statement, but this is one place where the mean value theorem helps us establish the truth of some statements. So we want to keep these two things in mind. They're two of the most important things to take with us out of this section. The sign of the derivative tells us about the increasing or decreasing nature of a function. Okay, well, let me look at a couple more examples here. We've got two graphs, two functions graphed here, and I'm saying that one of them is the graph of a function and the other graph is the graph of the derivative of that function. And I'm asking you to determine which one is the function and which one is the derivative. So I'm going to make a claim and then we're going to try to establish why that's true. So I claim that the red graph is f of x and the blue graph is f prime. So let's see why that's the case. And I'm going to come back and rely on these two statements up here to help me figure this out. So let's see what's going on. Well, recall when the derivative is positive, f, the function, is increasing. Well, where is the blue graph positive? Well, it's going to be positive for numbers up to -3. So it's going to be positive on the interval from -infinity to -3, and then it's positive for numbers beyond 3. Well, look at the function. Look at the red graph. The red graph is increasing on those intervals as well. So we see here, until I get to x equals -3, this function's going up. And then as well, from here, from -3 on, this function is going up as I read left to right. So these two things together can convince me that this statement is true. We can do the same thing for the decreasing part. So when f prime is negative, f should be decreasing. Well, the blue graph is negative only between -3 and 3. And the red graph is decreasing on -3 to 3. So again, between here and here, the red graph is going down as I read left to right. So again, these two things convince me that indeed this is the case. So I'm giving some justification for that. So the other important result out of this section is the first derivative test. And so I'm stating that right here. If we've got a critical point of a function, then we're looking at changes in the sign of the derivative. So if the derivative is changing, so if f prime changes from positive to negative at a point, then the function, then f of c, the y-coordinate at c, is a local maximum. So if f prime, so if I'm going from a positive derivative to a negative derivative, I must have hit a max. And likewise, if the derivative is changing from negative to positive at c, then I've got a local minimum. Excuse me. So if I'm going from decreasing and then increasing, I've hit a minimum. We can see that in this diagram up here. I'm going to erase a little bit. So here at -3, the derivative is going from positive to negative, and I've got a local max here. And then at this point right here, the derivative is changing from negative to positive, and indeed I've got a local min. Got more examples to work, and we'll continue in another video.